So in this example, we have a tank which initially contains 10 grams of salt dissolved in pure water, and seawater, which has a concentration of 3.5 grams per litre for the salt content, is delivered to the tank according to this equation, which is the flow rate in litres per minute, and it's a function of time in this equation, which is measured in minutes. So we're going to work through these different steps. The first one is to draw a diagram showing the tank and all the liquid flowing in and out. So here's my tank that I'm starting off with. We've got initially it's got 10 grams, so I won't mark that at the moment because it's not flowing in or out. But we do have seawater which is delivered to the tank, so that's going to be going in, and it's got that concentration of 3.5 grams per litre. So next up we have the flow rate. Alright, this is going into the tank, which has got some equation to it. So it's 1 over T plus 1, T plus 4, measured in litres per minute. So that's pretty much all we've got. It doesn't tell us that anything's leaving the tank at all. So that means that really all we've got is an inlet, and it's just going to keep on filling up and up and up. So we'll move on to part B, which is to now state the differential equation, which relates the total amount of salt in the tank, which we're going to call X, and time. Okay? So over here at B, the general equation that we need to fill in basically looks at the difference between the rate of salt flowing into the tank and the rate of salt flowing out of the tank. So this time, since we don't really have anything flowing out of the tank, that means that the dx dt out is going to be 0. So all we need to worry about is the rate of flow into the tank, and we should be able to get that from knowing the concentration of what's coming in and the flow rate of what's coming in. So we want to make sure that we have the units, okay, of X is the amount of our substance measured in grams, okay, and time we're going to measure in minutes, it said. So we want to make sure we're in grams per minute. So what we have here is the concentration, which is in grams per litre. And what we're going to find is if we multiply by the flow rate, which is described by an equation this time, but nonetheless is measured in litres per minute, what we will find is that the litres on the top is going to cancel with the litres on the bottom. So we're left with our equation looking like this. It's a little bit messy. Let's fix that. So that should just be T plus 4. So this is the number of grams of salt per minute that will be in the tank, dx dt. So in this example, we have a tank which initially contains 10 grams of salt dissolved in pure water. Salt water, which has a concentration of 3.5 grams per litre of salt, is delivered to the tank according to this equation, which you can see depends on T, and T is the time in minutes. So we're going to start off by drawing a diagram which shows the tank and all the liquid flowing in and out. So this here is going to be my tank. So what we're told for the flow is that seawater is being delivered, so that's going to be into the tank, and the seawater has a concentration of 3.5 grams per litre, and it's going to be put in at a rate which depends on time, but it can be described by this. And the units of that equation are litres per minute. Now nothing's actually flowing out this time, okay? So that's a complete kind of diagram for now. So we'll move on to question B, which is asking us to state the differential equation which relates the total amount of salt in the tank, X, and time. So inside here, we have some amount of salt, which I'll call X in. It's going to be measured in grams as well. So the differential equation kind of general form is for the overall rate of salt into the tank, it's going to be equal to whatever comes in minus whatever goes out in terms of the grams per minute. This is going to be measured in because X is the amount in grams and time we're going to measure in minutes. So since we just acknowledged that nothing was flowing out of the tank, that means that this term here, which looks at the outflow, is going to be 0. So the only one we need to worry about is what's coming in. And remember that we're trying to achieve it in grams per minute. So since we're given the concentration and the flow rate, all we really have to do is multiply these together in order for that to happen. So it's going to be the 3.5 measured in grams per litre multiplied by this equation, which is going to give us the flow rate. And that's measured in litres per minute. So the litres on the top and the bottom cancel out with each other. And we're just left with 3.5 over t plus 1, t plus 4. And that's going to be in what's left in terms of grams per minute. Okay, so this here is the differential equation, which is going to describe the rate of, or the amount of salt in the tank per time. So for part C here, we're asked what the initial condition for x of t actually is. So that means that initial, we need to look at what's happening at time is equal to 0. And if we jump back to our top of our question, it tells us that initially we have 10 grams of salt dissolved in the pure water. So that means that the amount of salt is just going to be this 10 grams. So x is equal to 10. So part D is now just to solve for the differential equation for x as a function of time. So we're going to start that off by looking for the general solution to the differential equation. Once we've got that, we're going to go back and reference our initial condition in order to get the unique answer to the differential equation. So we'll jump down here. The first thing that we want to do to solve this is to separate across the equal sign for the x's and the t's. So I think the easiest way to do that is going to be to put the the dt up to the other side. So we get dx is equal to 3.5 all over this, multiplied by dt. So once we've got our separation, as you can see, all the x's are here, all the t's are here, we should be able to integrate both sides of the equation. And remember that if it helps you out, you can think of this as 1 multiplied by dx. So this is pretty easy. If we integrate 1 with respect to x, we're just going to get x. This one here is going to be a little bit trickier because we're going to need to do partial fraction decomposition to be able to integrate it. So I'm going to do this as a little bit of a sidestep over here, and then we'll come back. So to do our partial fractions, partial fractions, what we want to do is start off by setting up our dummy fraction. So we're going to say that this expression that we start with is equal to some constant a divided by the first factor, which is t plus 1, plus a second constant b divided by the second factor, which is t plus 4. So we need to figure out a and b. So how I'm going to do that is I'm going to get a common denominator across everything. So the common denominator is going to be this one here, the t plus 1, t plus 4. So if I want this one to have t plus 1, t plus 4, I'm going to need to multiply by the t plus 4. So multiplying by t plus 4 on the bottom line to get that common denominator, I also need to do it on the top line to keep it equal, because these cancel each other out, which means that I just have essentially what I started with. So this line and this line remain equal. If I do the same thing for my second term, this one needs to be multiplied by the t plus 1 part to get that common denominator, and I need to make sure I do it for top and bottom line so that it remains equal. So now everything has this common denominator. They're all going to cancel each other out if I just multiplied by t plus 1, t plus 4. So what I'm left with is just what's on the top line. And I need to now go through and figure out what a and b are. And the easiest ways to do that is just to pick some convenient values for t. So the first convenient value I'm going to pick is t is equal to -4, because if I sub that in here, I'm going to get -4 plus 4, which goes to 0, and it should knock out this a from the equation. So let's go ahead and do that. Okay, so this becomes 0. 0 times a is 0, so it goes away. So I'm left with 3.5 is equal to, this is going to be b multiplied by -3. So 3.5 divided by -3, this leaves me with about -1.67. if I go back and repeat this process, but with a different convenient value, I'm going to pick t is equal to -1. Oop, so let me write that. So let t equal -1 and sub it in. So we're going to get this. Alright, so -1 plus 1 goes to 0. 0 times b disappears. So we get 3.5 is equal to a. This is going to go to 3. So a on its own is 3.5 divided by 3. And this is going to go to positive 1.67 approximately. So using both of these pieces of information, what I can say, I'll pop it in up here. A was equal to positive 1.67 and B was equal to negative 1.67. So what I've done here is rewritten something that was a bit messy in terms of two terms, which I'm now going to be able to integrate quite easily. So let's transfer this information back to what we've got working through our problem. So we need to integrate rather than writing it like this. It was 1.67 over t plus 1 and then negative 1.67 over t plus 4 with respect to time. So when we integrate this first part, the 1.67 can stay out the front. It then goes to the natural log, of what's on the bottom line. This one, again, the constant stays out the front, and then we get log of what's on the bottom line. And because we've done an indefinite integral here, we need to make sure we pick up the plus c on the end. So all of this here represents the general solution to our differential equation. And it's general because we don't at this point know what c is. Any value will technically work out and be a solution to what we started with up here. So what we want is not just any general solution though, we want the specific or the unique one that meets our case. And how we get that is from our initial condition, which we identified above. So we have for our initial condition at t is equal to 0, x is equal to 10. T equals 0, x equals 10. So if we now substitute this in to our solution, we should be able to figure out what c is. So 10 is equal to 1.67 log of, t is going to 0, minus 1.67 log of 0 plus 4. So it's going to be 10 minus this plus this in a calculator. And that means that c becomes 11.62. So if we go back and pop that into our equation, we end up with our unique solution to the differential. So from this, we should be able to figure out how much salt is in the tank at any given time just by substituting that time t in. So this here, our unique solution, is the answer to the question. Of course, if you wanted to, you could always plot this as well in order to look at how much salt X is in the tank at any given time t.